Good afternoon, everyone. My name is, and welcome to another SUZI lecture. And we might have one more this year. My name is Svetlana Berzev. I'm a former president of SUZI and a member of the educational committee, which organizes our lectures. Today, we have a pleasure and we have going to have an excellent presentation by a good colleague, John Sherstobitoff. I would like to introduce him before he starts. We could spend 10 minutes talking about his works and achievements. He has vast experience, more than 40 years of structural engineering experience in practice. He has worked, he specialized, of course, in seismic design and retrofit of structures. Today, he's going to talk about one of type of projects that he has done, and those are water storage reservoirs. But he has done many, work on many other structures, including schools, industrial buildings, and then other very important public buildings. I know right now he's working on seismic retrofit of the Canadian Parliament in Ottawa. And so very diverse experience with excellent background, and has been for 10 years the chair of the Seismic Code Committee for Canada, the Developed Seismic Code of Canada. And he won numerous awards for his work, which he well deserved. I had a pleasure and privilege to work with John about 30 years ago when I first, that was my first consulting and the only position in Canada. And it has been a great pleasure. So without further ado, I would like to invite John to start this lecture. Thank you, John, for taking time early in the morning in your time zone. Welcome.
Well, thank you for that introduction, Svetlana. And yes, no, it's a pleasure to chat a little bit about one aspect of the work that I do. And again, hopefully the screen is showing up well for you. Yeah, right now I'm with the firm Osenko here in Vancouver, and I'm the principal of seismic instructors. So today I'll talk about both the design of new reservoirs and some seismic upgrades of existing reservoirs. To give you a bit of a feel of Greater Vancouver. This is a cartoon of the water system. We get the water from natural reservoirs. It gets eventually gets through to the storage reservoirs out in the system and gets out to the public. And again, we supplies water to 2.7 million residents in Greater Vancouver. So these are our three reservoirs up in the hills. They're protected from the public. So again, it starts out with very, very clean water that we get that's coming down to the residents. So I'm going to go through four different reservoirs: new construction, some above ground, some below ground, and then seismic upgrades of five different reservoirs in the system, both conventional and with viscous dampers. So this is just an example of an above ground reservoir. If you say what do our reservoirs look like here? This is a recent one, and I'll chat about that more. I mean, the inside of the reservoir is pretty typical. Again, these are all concrete two-way slabs, columns, valve chambers. Valve chambers are pretty spacious in the reservoirs nowadays, with overhead gantry cranes to service the equipment. And as I mentioned later, we've had architects on board, to design these above ground reservoirs to add some interesting features. This reservoir is going to be at the intersection of two new roads. We've got a water fountain in front of it, and there's going to be tennis courts and the like on the roof. So the above ground reservoirs have much more design features, landscape, and architectural involved. 29 reservoirs in the Greater Vancouver system. Again, the three mountain water storage being transmissions. Another interesting talk. There's 7 crossings underwater that are designed for 1 in 10,000 level earthquake, and we did one of these So yeah, we've got to get water down to the southern part of Greater Vancouver through those. But in the interim, every day the reservoirs are filled up at night, and they're used during the day to augment supply to the residents. So for those of you not familiar, a seismic hazard here in BC, typically for new design, it's based on just one hazard level, 2% in 50-year probability of exceedance, or the annual exceedance probability 1 in 2475. Again, you can sort of see the heat map. Vancouver being on the coast, and it gets worse as you go west towards Vancouver Island. It's a probabilistic combination of three different earthquake sources that we have. Magnitude 9 subduction offshore, 7.5 subcrustal, 35 to 50 kilometers below Vancouver, and then a crustal, 10 kilometers or shallower. Again, long duration and short duration shaking. Currently, we have the National Building Code 2020, and there's going to be no change in the seismic hazard values for the next 5 years at least. As we all know, seismicity changes with better science every 5 years, and we'll have at least 10 years of stability here in Canada. Again, another interesting thing that's happened recently is that the seismic hazard now is based on, you just need to go to an online tool with a latitude and longitude, and if you have your VS30, you'll get your design response spectrum for that site. In Greater Vancouver, we've had a seismic microzonation project here for quite a number of years, and that's just going to be released very shortly, where you'll be able to, with a latitude longitude, get an estimated VS30 with no borehole work, to do some preliminary designs. And this is just a snapshot of an early map for the Greater Vancouver area. So this is going to be very useful, but the VS30 has made a big difference in the design. So you can see a National Building Code of 2015, that was the previous one, and it was updated in 2020. In 2015, we had the step functions. If you're in site class C, you had one value, regardless of if your VS30 was low or high. In 2020, it is now gradational. You put in any VS30 and you'll get a unique response spectrum. And you can see the comparison. And in blue is the 2015 seismic hazard curve for Vancouver, site class C. And in 2020, there's now the range from VS30 of 760 up down to a softer soil of 360. So there's huge value now in Canada to get a VS30 for every project, because you could be less than the previous code, you could be more than the previous code, and this is a big improvement in the current code here. And just to show you, again, I just did this for sort of comparison. You can see the kind of spectral acceleration values here we have, in the Vancouver range, at 0.2, 0.5 seconds in the 1.1, 1.2 range. And as you go west on Vancouver Island, on site class C soil, it could be as high as 1.9 P at the 0.2 seconds. So yeah, so we're in a fairly high seismic zone here, compared to other parts of the world. So for a new construction, Metro Vancouver, that's the entity that controls all the facilities in the area. Again, that 1 in 2475 level earthquake, post disaster for the reservoirs, and this is their criteria. It must remain fully operational after the 1 in 2475 with just minor damage, retain its strength and stiffness, the walls, near elastic response, and the reservoir roof and other ones, again, minor damage, but anything so repairs can be completed with no interruption of the reservoir being filled and emptied on a regular basis, even immediately following this design level earthquake. So a fairly high level performance level requirement. So the standards that we do here, Canada has no guideline for water retaining structure. Like we don't have a guideline that says this is how you design water reservoirs. So we use a compilation of a variety of sources. So the seismic hazard, the BC Building Code or the National Building Code, which I showed you the hazard on the previous slides. The design requirements, we use ACI 350, and then we detail the concrete to the Canadian standard A23.3, and using the latest versions of each. So As I'm sure you're all aware, when you start mixing and matching codes and hazard levels and the values you're using in each of them, it takes a lot of care to make sure there's compatibility between the values you're using in the equations in each of these standards. That's a big effort to make sure that what the ACI expected is what we're using in these equations. So again, standard loading that we use for new reservoirs, dead live snow, roof loads. As you can see on the roof of these facilities, a lot of them are parks, and so we can have very high loads. We can have vehicle loads. We have bus loads driving on the roof, and then if it's just a private reservoir with no public use, then it's down as low as 1 kPa. Like I say, yeah, there's we have one reservoir where we have the largest buses and dump trucks and almost anything is allowed to drive on the roof. Thermal is a condition we check on every new reservoir design, and the water inside the reservoir changes from 18 to 3 summer to winter. And the ambient is 27 to -8. So you can imagine we can have a completely different induced bending moment in the walls if they're exposed to the environment in summer and in winter. And we design for both those conditions, and starting with an assumed average temperature during construction. Just some strain and coefficient of thermal expansion values. And typically now, because really to try and get the best concrete mix to minimize shrinkage, minimize cracking, we design different mixes if the concrete is placed in the summer and if it's placed in the winter, because again, in the winter, we cure it at 10 degrees. In the summer, we try to keep it cool to a certain level, and we have very custom mixes for each season to optimize crack control. And again, we have typically a concrete material specialist on board, again, trying to minimize the effects of early age crackage, long-term shrinkage, and again, these seasonal thermal effects, all with a target to have crack 0.2 millimeters or less under all that design loading. Earthquake, soil, fluid, and again, so we talked about the spectral acceleration values, the ACI. For those of you familiar, there's the SRSS combination of inertial, vertical, convective, impulsive loading, inside the reservoirs. The vertical acceleration to amplify or change the effective weight of the structure and the hydrodynamic pressure. And again, the impulsive and convective effects of the large volume of water, either the high frequency effect of impulsive or the low frequency with the sloshing effect. We typically assign additional mass to each of the columns in the reservoir. The Zanger effect of the equal volume of the columns, just to check any out of plane effects on the columns themselves. And again, in addition, there's the hydrostatic water, the lateral soil pressure, outside the static and dynamic, because many times they're partially buried or fully buried. And we check all of those load combinations that I mentioned for if it's in an operating condition of maximum normal operating water level, half, or empty tank, because we never know what condition it's going to be in. I won't go through this in detail, but this is an example taken from one reservoir, and it does vary by reservoir, whether it's underground or above ground. And so these are, for example, the 13 load combinations that we'll use in our 3D response spectrum analysis. And like I say, it really captures all the effects that I had mentioned before. And you'll see that thermal is important because of the water temperature changing on the inside, and usually a portion of the wall is exposed to temperature on the outside. And this is just illustrates that the three conditions that we do, for the full combination of service loads and the full combination of earthquake loads. And you can see, depending on the amount of soil, depending on the amount of water, depending on the temperature, there's a lot of different load combinations on the roof, the walls, not so much the columns itself. And again, there's that rule for the SRSF combination of the various internal loadings. As I said, we do full 3D models all the time. And again, a variety of way of just, putting the loads on there. We also model the soil properties because we find that has an impact on the wall rotations and some of the demands at the base of the walls. So we always model again, and typically these reservoirs, the base slab will be a solid and integral with the walls. And so the effect of having that flexibility of the soil is important to get better understanding of the demand of the walls and the base slab itself. One of the other things, of course, when we design these, we design for freeboard, so we don't have that sloshing effect, doesn't induce upward loading on the roof slab. Again, that loading pressure can get very high, and can, again, if it's not careful, you can get damage to the roof slab due to that high upward pressure. And again, sometimes we just can't avoid it, and then we just have to design these corners for that high upward loading of the sloshing fluid. But we always typically the freeboard is in about 550 millimeters typically works. This particular reservoir, we didn't have the luxury just due to height restrictions, and we had to design for uplift pressure. Okay, so I'll go through those four new reservoirs just to give you sort of a feel for them. Fleetwood, you can see some of the volumes there, 14 megaliters. This is one that's underground. This is under construction as we speak. This is a photo that was just taken a few weeks ago. Again, the standard two-way slab, raft, complete raft on the base slab. So it really is a complete integral concrete box with no expansion joints anywhere. And you can see the dimensions in plan, fairly shallow water depth compared to the plan area, but sometimes, in this case, this is in a park, and so we had to stay above the water table and stay below the soil in the park level, and that's just what we had available. So this is, you can see it's an illustration of where it's located in a public park, which we've taken over during construction. The cell sizes, the valve chamber in the middle, a little access building on the top. And typically these are always designed for future expansion on one end. So in the future, as they need more storage, if the population grows, we'll be able to double the capacity of the reservoir. And this is very typical in almost all the reservoirs. This is a cross section, but again, you saw some of the photos. We've got these, I think they're very, very nice valve chambers now with the full overhead crane to be able to service the valves and take them out for replacement or servicing. Well, of course, we have the fully resistant marine doors to provide access to and from the chambers during maintenance. We have roof hatches with actually two levels of protection. We have one roof hatch, and then we have another roof hatch, and they're both locked to prevent the public from ever gaining access through the roof into the reservoir. So that gives you sort of a snapshot of a typical cross section. So the base slabs here, again, everything is, and it's F61 approved, the concrete for the base slabs. We use shrinkage reducing admixture. This is just an example of the one we used on this project. We also put in the Kim admixture to promote self-healing of small cracks in the future. And again, when the project is complete, the contractor feels they're done. All cracks are fully mapped. Every crack is mapped, location and width. Every crack 0.2 millimeters and larger is injected as part of the project. That's part of the design basis, and that's what the contractor's scope and their cost. These are all injected, and we use a polyurethane grout. And here's some examples of the ones that we accept or approved equal. All NSF 61 certified. And again, when all the cracks that are less than 0.2 millimeters that are mapped, at our discretion between us and the owner, we inject a number of them especially when we do the hydro test and we see any through thickness leaking in the walls. Of course, we never backfill until all the hydro test is done. And if there's any through thickness leaks, we'll inject all those cracks fully as well. It's interesting that we have, of course, in the base slab we have crack control joints, and the sealants that we use there during disinfection before they put the reservoirs into service. They use a very, very high dose of concentrated chlorine, and these joint sealants have to be able to sustain that, because if you don't specify the right product, those can start to deteriorate very quickly, especially if they're subject to this dosage once a year during maintenance. Again, we always do a patterned pour at the base slabs to minimize cracking. So we just pour them in alternate patterns, let them shrink freely as much as they can, and then come along and close those up. And then we have that sealant that I mentioned at the joints. But again, they're fully connected as far as a reinforcing steel to make it an integral mat. The perimeter walls, again, similarly, of course, the concrete's NSF approved. It's interesting. I'm sure those of you that are involved in this recently, it's much, much more rigorous than it used to be. All the components have to be NSF certified. You have to actually do the mix design, do some testing of it, submit it for approval. And so to get appropriate bidding on our project, we had 3 local concrete suppliers get pre-approval of their concrete mix designs, both the summer mix and the winter mix, so that we know that whoever was successful in winning the project, there was no delay in getting the project started. This process to get certified took many, many months for these concrete suppliers. And the mix design also contained the KIM for the walls for this long-term self-healing. Similarly, we did a pattern pour for the walls to minimize any shrinkage effect. Obviously, if it's all one concrete monolithic box, we can't pour it in one unit, or the cracks will really tear it apart. And you can sort of see colors of green to red and yellow. These are the pattern pours that we did. So it allowed the contractor to pour up to 1/3 of the walls at any given time, but they did it in a sequence that was appropriate for them. And then finally, the roof, similar, because again, it's a concrete monolithic box. So now the walls are poured, the columns are poured. And then what we would do is we would pour the roof structure in its entirety, but we would leave, between 1 and 1.2 meter closure strip around the outside. So we pour the roof, allow it to shrink and cure freely away from the walls. And then, under a very specific temperature control, hoarded control, the closure strip, well, then we would pour it at a very controlled temperature. And again, then to try and control the shrinkage here to connect it to make it a monolithic box. And similar was done for the valve chamber roof, but I won't go into that. So at the end of the day, you get it's really good from a maintenance-free monolithic concrete box. Well cured, minimal cracking to deal with all those loads that I had mentioned. This is a photograph of in the park. Right now, it doesn't look like that, but eventually we'll restore the park to where it started to. We'll have some First Nations art work on the access building. And, for these reservoirs, because they are usually in public spaces, on these projects, I'm typically the project manager and the structural lead. And again, managing a design team of our structural, civil, electrical, instrumentation, both mechanical, HVAC, geotech, concrete material specialist. We have an architect, landscaper, environmental specialist, arborist, noise consultant to keep noise during construction to a minimum level. We have, noise barriers that we put up that are fully 3D modeled. Coating specialist, corrosion protection for the piping, and a constructability reviewer. So it's a big team. It's a big team during design of these reservoirs here. And because of that, we go through. It's interesting on these projects. We go through a full conceptual design, full preliminary design, and then the full detail design. And then during construction, we have a full-time resident engineer during construction. So these are very good projects from an engineering point of view. And really well well integrated with the community and Metro Vancouver's design team. This is Jericho Reservoir. This is now above ground reservoir that was completed recently. And you'll see, now we've got architects involved. That's the first time I've done a reservoir. We've sloped the walls inward by 5 degrees because the architect thought it was a nice effect. Nothing is straight on the outside. It's all sort of panelized with, different form liner was used to get a pattern on the walls. And again, for this one, because this will be in a very public area in the future, we designed this nice water feature at the corner, sort of tie into the water reservoir. Again, like 56 different custom fountain lights and stuff. It'll be a nice feature when as the neighborhood gets built out with the residents here. And again, you can sort of get a feel of the volume of the plan. Each cell, it's 2 cells, 40 by 40 meters each, and 7-meter water depth. And as all the other ones, designed to double the volume out one edge in the future. Helling, this is another above ground one. This is a rendering. You can see again the same kind of architectural features. Two-tone concrete. It's going to be dark concrete to a certain level, panelized with form liner and plain concrete. And again, you can sort of see here, this is a round tank that's there today, and this is going to hugely increase the volume at this site. So again, this was designed for a certain volume. You can see about 60 meters long with a varying width, deeper water. But this went through a tender. We went through again all those levels of design through tender, and we just hit the tables tendered at the peak of height of construction costs here, and so they put it on hold. And what they may do is revisit it in the future and actually do that expansion at the same time at a future date. You'll see in plan, as in the next slide, this is a very irregular reservoir in plan. And for all those loading combinations, we couldn't get it to work without putting in a liner. We don't like putting in a liner for maintenance purposes. We just couldn't get the crack control to work with that. So you can see this is an existing tank. You can see the shape of this reservoir. It had to fit into a property that was there. And again, because of that irregular shape at all these corners, we just couldn't get it to work without the liner. And again, you sort of start to see that, the landscaping that's involved in all these lots here. These are houses with their back fences, and their backyard is right here. So this was right in the middle of a neighborhood, and in an aerial view, you can see this is where the design for the tank was, and there's houses all around it. And so the public open houses for this was really fun to hear from all the neighbors as what they liked and didn't like about the design appearance. Again, typical cross section, fully monolithic structure as before. The 5-degree inward leaning wall to add a bit of interest for the public, and here it was going to be a private roof. No public use. One of the first reservoirs that I was involved in, a Little Mountain Reservoir, is reconstruction. And so this was a very large reservoir built in 1911. We expanded it to 175 megaliter reservoir. It was the largest in Canada at the time. And again, this is the one that is allowed to have buses driving on it. It's in the middle of Queen Elizabeth Park in Vancouver, for those of you that know it. And again, you can sort of see that each cell is 85 by 78 meters. So there's 2 of those, water depth, a fully integrated monolithic piece of concrete, and that's just sort of a rendering of where this is in the park. So this was a really interesting project because this was all the concrete that we demolished, 10,000 cubic meters, was recycled. All the new concrete was high volume fly ash, 50% or more. And again, is really the state of the art at the time here in Canada. And again, they do their calculations of more fly ash you can use instead of cement. It really does help with contributing to reduced CO2. They said more than mostly 50%. again, this stuff, of course, the trouble with that fly ash, it's sticky, it's difficult to work with. The delays, it takes longer to set. So the contractor was doing the finishing of the concrete at midnight or 2 a.m. in the morning, in the middle of a neighborhood, but that's just what it took. But again, lower curing temperature, it really helped on reducing the shrinkage and really helped on reducing the permeability. So a lot of trucks on that project. Is a very large project, but extremely high quality concrete. So I've just got sort of a series of photos here. This is where it started with. Again, not really controlled access to drinking water back in the day, compared to now our very secured reservoirs up in the mountains. They put a roof on it, in the 60s. Again, this was all precast concrete, and it turned out to be very poor quality, and it was kept deteriorating. And ultimately, we're gonna replace it there. Again, I mentioned some of the size here, close to 200 meters by 100 meters wide, with no expansion joints, and that was the cost back in the day was a bargain for that size of a project. Again, as I mentioned before, thermal expansion, of course, was critical here because we analyzed all the thermal stresses. We had the mechanical engineers work, with all the insulation on the roof. We had the thermal gradients on the roof, the walls, the water temperature in and out, and did all that expansion with the, as I mentioned, the foundation springs at the bottom as well. And again, this is sort of as I mentioned before, the 3 to 18 water on the inside, the insulation, the membranes, the concrete topping, the surface, and we ultimately got a design, a through thickness gradient in the roof slab to design for. So just some snapshots in time. I thought this was interesting. So this is when we started demolishing the project. 2 months, we got to this stage, demolishing and shipping everything out for recycling. You can just see the huge amount of effort to get this large volume of concrete demolished and sifted. 6 months in, we're already starting, new construction. Everything's demolished and cleaned out. Starting construction of the base slab, the columns, the perimeter walls. And again, the pattern pour of the concrete slab, starting in sections here. They had these gantry cranes. It was fantastic to ease construction. This was really effective to expedite construction. Rather than try to have one tower crane, just wouldn't work for a reservoir of this size. Again, building up the walls, in there. Again, the pattern pour of the walls. You can see one's poured, the rest are under construction. Again, we had one corner that we couldn't excavate because of the rock. We didn't want to, and so we're chipping in to put in the foundations there. Some Vancouver weather that year during construction. We used silica fume shotcrete, on that surface. And that turned out to be very nice in the corner, because again, next to this conservatory, we couldn't do anything different. Again, the contract here was very clever because all the columns were designed to have these metal inserts, and so there was no shoring posts in the reservoir at all, and they had forms that they could support off the columns, and then they would just keep sliding these down as they did panel pours of the roof. So between the gantry crane and the sliding roof forms, it was a very, you can see the cost was very effective, and it was very quick to get constructed. Very clever contractor on the project. And again, the roof slab going in, and the roof membrane going in, and you can see it's at the high point of the city in Vancouver to deliver water by gravity to the residents. Our reservoirs are up in the mountains up here. And again, that's the valve chamber. Of course, at the end of the day, the heart of this is to get water in and out of this, and that's always a tricky part of and a fun part of the project, to get all the thrust blocks for the piping, and try and squeeze everything into as reasonably small a space as possible. And again, because back in the day, with high volume fly ash, a lot of national and local awards for this project. Okay, seismic upgrade. Again, a lot of existing reservoirs, they're designed back in the day. Codes have changed a lot. And again, the intent is to upgrade them to that same performance level as a new reservoir, fully functional for the 1 in 2475. And again, so these, we all go through the analysis, we assess these. Metro Vancouver has a very detailed flow chart to determine, is seismic upgrade the best approach, or is it better to replace it in situ like we did for Little Mountain? Most of the existing reservoirs are what we call a hopper style, you can see here. So there's these perimeter walls, usually backfilled to nearly the top of the wall, the sloping of concrete down the slope. Again, columns, there's usually expansion joint in the middle. This is a floating, it's a one-story moment frame roof structure, column and roof slab, expansion joint here, sliding joint at the top of the wall. So again, a lot of maintenance issues in these to keep these expansion joints working, and these were usually open to the public, on the roof. So usually 2 or more structurally independent units, short columns, tall columns, all the kind of things that are not so good in an earthquake performance. And that just as a detail of the typical existing walls, the sliding joint, at the roof, and the kind of expansion joint that was there with about a 50 millimeter gap and again, this when you did it for this flexible wall, these would be pounding during an earthquake as well. So typical deficiencies: the perimeter wall, sliding, bearing, overturning, in plane shear, out of plane shear, and bending. And again, usually they were deficient. The roof column structure, again, so this one-story moment frame. And again, it's either the columns or the roof slab or the rotational demands on the footing slab, because these reservoirs did not have a monolithic base slab. It was just a small footing, and then the slab on grade was cast into it with a lot of sealant and jointing. So to keep this really water, to try and keep as much water in the reservoir after an earthquake, to keep the rotational demands at the footing down, so all the sealants wouldn't be compromised, after that 1 in 2475 earthquake, and of course then the pounding of these independent structures. So the first one we did was Kirtland Reservoir seismic upgrade, 74 megaliter, big reservoir, and it had 2 different cells. This cell on here, constructed in 55, 2 units with an expansion joint. The cell 2 with 5 independent roof unit with the expansion joints, and again the surface is open to public use, but the rest of it is underground. And again, this is just downstream of Little Mountain in a very public park. So we use 2 different approaches in the 2 different structures just because of the way they were built. And again, you can see the size of it, 100 meters by 47. So we connected the roof units together. And here, because it was a moment frame, just due to the nature and the size and the rebar that was there before, we just put in a new series of a grid of beams at mid-height of the existing columns. So we basically created a 2-story moment frame instead of a 1-story moment frame by putting these in, and this solved the problem for our moment frame, and we left it disconnected from the roof. And now we just had one large structure, still not connected to the perimeter walls, and upgraded for that 1 in 2475 level earthquake. And again, I typically, just a fairly easy means to connect the roof slab together. So cell 2, this large one, we connected all 5 together, with this detail. So now we had one monolithic roof slab. And here it was more cost effective just to put in 4 large ductile concrete shear walls, 2 in each direction in a nice pattern to minimize any torsional eccentricity. So they were laid out in a nice location. Very long drag struts to connect to the roof slab, because the roof slab had a nominal capacity. I remember we used Hilti anchors. We fully tested, all of these. To make sure, and they did special testing for us here from a deformation point of view, to make sure that sort of that shear lag that we got the load out to where we thought we got it to in the reservoir roof. So this was, again, it was fairly quick. These reservoirs can typically be taken out of service for a few months over the winter because they've got 29 reservoirs in the system. They can transfer water around. So it is cost effective to empty it for a few months, build what you need, and get out. And again, these were tuned so that the inelastic deformation of these ductile walls match the capability of the existing concrete for their deformation. So we didn't have to touch these at all. Another one, Vancouver Heights. Again, similar reservoir. Again, what we learned that, these others typically, the perimeter wall didn't work. So the foundation was enhanced with soil anchors, foundations, shotcrete on the inside. So that strengthened the perimeter wall. The bases of the columns, these ones had to be strengthened a little bit. And then again, we put in those 4 interior ductile concrete shear walls as we did for Firstland. So again, fairly large size reservoirs to get together to have a monolithic roof. 4 walls are very effective to upgrade. Next one that we upgraded was Central Park. You can see that, the volume, the sizes here, they start to get quite typical. 1974. So here we moved to we assessed both conventional options, the ones that I showed you before, and then we looked at both friction dampers and viscous dampers. And this is a project that Svetlana and I worked on together. As you can see in the picture, ultimately viscous dampers were selected as the preferred method here. And again, I think for those of you that aren't familiar, fluid viscous dampers, they really increase the critical damping ratio. So that response spectrum, it can drop significantly. So the effective demand on the structure goes down. There's a large variety of these. The earthquake's energy is dissipated into heat as this piston moves through, and the silicon type fluid and moves through the orifice. A whole bunch of variety of designs on this one. The beauty of this for a reservoir is that the roof could expand and contract winter and summer. And again, it really has no induced stresses because these would move, they would accommodate that movement with no induced stress. And again, the force, the resisting force, which is proportional to velocity, it really effectively adds no stiffness to the structure. So from the response spectrum point of view, you're not sort of pushing yourself up the response spectrum curve to get more demand. And so it's the beauty of this is it's out of phase. The most resistance is when the structure is right at zero deformation. And when it goes out to maximum deformation, there's no force. So when it's flying through at maximum velocity is the maximum resistance and energy dissipation. And again, using a non-linear viscous damper, 0.4, the CV to the alpha really is sort of a preferred one. Because again, you don't have this, if the earthquake is larger than you expect, you understand it's going to keep tapering off with this non-linear behavior. Always designed for the upper and lower bound of plus or minus 15% of what we think we're designing it for. For these ones, we tested it because they were outside. We tested it at cold weather. We tested it at minus 20. We tested it at plus 30 in a very specific protocol. In this case, I was there to witness the testing. And even though I've got photos, Taylor Devices was the one that helped us all the way through. And then when we bid the job, unfortunately, they lost the bid to Anodyne. But they continue to be an excellent resource for us on viscous dampers on many, many other projects. On this project, we kept spares on site. We kept 2 spares on site in the same temperature regime as the real, and we tested those every 5 years to confirm that they stayed within these bounds, and they did. This really isn't done much anymore, but this was sort of early on in the use of these, and we thought, we can do it for the sake of a few spares. We put those and tested them. And nowadays, there's many vendors, very good competition, a lot of unique ones. So again, it's a very robust industry nowadays. So for this one, this project, we did have to reinforce that perimeter wall. It just didn't have the capacity that we needed. And then, of course, for the viscous dampers, they were placed outside the reservoir. You can see the soil level outside, just doweling in a little concrete piece. The viscous damper is in and out of the page, connected to the roof, connected to the wall. So, during it had full gimbal joints at each end, so thermal expansion could be accommodated in two directions. The earthquake load, as the roof moved in either direction, and dissipated the energy as the roof moved in and out of the page. The damper expanded, contracted, and dissipated the energy. It was a very effective system. No pier walls in the basement or in the bottom of the reservoir. So again, using viscous dampers for upgrading of existing non-ductile concrete. We've used it for other projects, and is to prove to be a very, very effective means. So minimal disruption. This was the first use of viscous dampers for a seismic retrofit in Canada, and of course, many more used after that. So, a few years later, Cape Horn Reservoir by them, similar dimensions, 4 units, roof units. We connected them together, and we used viscous dampers to upgrade that as well. It was interesting note here, the St. Louis water staff visited us, Sandwell, back in the day, because they thought this was a pretty neat solution. And so they upgraded their large reservoirs in St. Louis using viscous dampers after visiting Vancouver and seeing how it was done here. And then 2 further reservoirs were upgraded using this technology. So I just wanted to quickly, just a few slides here again. And I don't know sure what you do in Kirby as far as new design with supplemental energy dissipation. We now require full 3D models, nonlinear time history analysis, 2 suites of 11 ground motions, all 3 components, and we design the structure to remain elastic for mean plus the important factor times the standard deviation for each suite. So again, we're taking quite a robust approach. We're really trying to keep the structure to have no damage after a 1 in 24/75 earthquake. But this is what we're now doing if we were doing a new reservoir with viscous dampers. This is what we would be doing. And just a few references to close out. This is a paper that Svetlana and I wrote for a conference. Again, I put the link here. You can download and read that. Svetlana, we must have been teenagers when we wrote this back in the day. And then the National Building Code of Canada. If you're interested in any of the requirements we have for supplemental energy dissipation, a lot of pages. It's a free download, but supplemental energy dissipation you can find in these sections. And again, we have a very, very good commentary. It was completely redone. It's going to be released very soon, and it has very good background for this. And again, lastly, thanks to Svetlana for inviting me. Metro Vancouver, they provided several slides and allowed all this information to be shared, and my colleague Brandon Wong for assisting with the presentation. So thank you very much. And if there's any questions, happy to take them.
Thank you very much, John. This was an outstanding presentation. So Svetlana and I agree that I will convey the discussion part. So please, the audience is free to pose any questions you have regarding the topic. As always, I can be the one to break the ice.
Sure.
Yeah. So I'm kind of interested in the convective modes, or to be more precise with the consequence of the sloshing wave height in the closed reservoirs, the ones which have the roof. So the heights of some waves which I calculated in some projects were like between 15 and 40 centimeters. So I guess in this case, when you have the roof, you have to take that boundary condition into consideration as well.
Yeah. So 40 centimeters, 400 millimeters. Yeah, the recent reservoirs, we had a 550 freeboard, so we just avoided that upward effect. So there was one reservoir we could only squeeze in 250 freeboard just because we were limited in space. And again, there's some, I didn't put it here, but as you know, there's some very good references as to how to calculate those pressures in the corners. And again, with a monolithic concrete structure, which is what we're using now, it really wasn't that big a deal. Knowing it was there, it's not a problem. And it's interesting on the existing reservoirs, because there's so much redundancy in the system, we now had an operating level where we had the proper freeboard because we didn't want to be reinforcing those existing roofs that were floating, because otherwise, those would be blowing off in the corners. And we had the luxury of reducing the normal operating level to provide the allowable freeboard, because there's an overflow level and then there's all this stuff. So there's always an ability to tune that in the existing ones, so we didn't have to redesign the roof to accommodate that. So we had that luxury here with this really nice redundancy in our system.
Yeah, that's good news, because the problem can be big if you cannot reduce the operating level of water. So forces are very high.
Or you have to understand that if the trouble here is if the corner blows off and you got to keep the water safe for the public, you just may not be able to use that reservoir. Here the health authorities are very, very rigorous as to when a reservoir can and can't be used for potable water. And every new project, of course, we have to go through the health authorities to make sure they're satisfied with how we're protecting the water in each reservoir. So it's a very rigorous system through the health authorities here.
Yeah, I see. Thank you. And one more question from my side. I saw that you mentioned the crack limit of 0.2 millimeters. Is it like a general condition, or you had some more stricter conditions in some situations?
No, that's our target. We found, because as I mentioned, if it was, at the end of construction, if it was 0.2 or more, those were all injected. So we know that when we left the job, the cracks were 0.2 or less. Any through thickness leakage, even down to 0.1, we injected all those as well. And again, with the KIM in the concrete for self-healing, it was interesting that we would find, when we did the hydro test and you'd let it sit for a week, and then we do our measurement of the loss of volume, we started to see cracks start to heal. So that was just a target that we've used. We found it's been very successful. At the end of the job, when we have our, I think, 1/2000th of the volume is what we're allowed to lose in 3 days. And it works. I mean, there was no leakage out the base slab, the walls for that one. I think it was 3 millimeters of loss over the height of the water. So it worked for us. And if we can keep it within 3 millimeters of loss over 3 days, that was working for us.
Yeah, that's very good, because back in the day when we had some old design codes, the limit was 0.10 millimeters, which was very hard to achieve. Now in Eurocode, we have the limit depends on the ratio of the water height and the thickness of the wall. So basically, the thicker the wall, the more relaxed the condition. But the 0.2 is still pretty relaxed in terms of the European practice. This one, which is forced now.
But like I said, we found it works very well just from your reality as to keeping the water there. And again, I'm sure all your reservoirs, we have under drains. If there's any leakage during the life of the reservoir, we know exactly how much water is getting through the base slab. We have perimeter drains at the base of the walls, separate from the soils. If there's any water getting through the walls, we have a system to take it down to those drains, and that's monitored in the valve chamber. So we know how much water gets through the base slab. We know how much water gets through the walls. And if we see things are deteriorating, we have at least the ability, to try and repair it. But to date, it just hasn't had to be done.
Yeah, that's very good, because we monitor the situation, and the 0.2 makes sense because the concrete tends to self-heal. I don't know, several weeks it needs to self-heal the 0.2 because of the calcium and the water and everything. So I hope that the European practice will be more relaxed in the future, because it's for the designers and also for the constructors, it's very hard to achieve the very strict levels.
I agree.
Okay, thank you for now. So anyone else?
Julie, I have a question. If anybody else has from those present, I Happy
Yeah,
to.
one short question regarding this. If I can, Svetlana, before you.
Yes, please.
Yeah, thanks. Regarding this fluid viscous dampers in the project that you did together, so with
Yes.
how much was the capacity of the stroke of the dampers, and how did you place them? Because I'm not sure, I didn't catch the, let's say, the shape, and where did you place it, let's say, to capture the position? Yeah?
No, very, very good question. And yes, I knew that question was going to come up, and I didn't have time to go back through the spec to get that. But I will send that information to you. But the stroke was fairly small. The stroke was about plus or minus 75 millimeters, if I recall. Okay, the stroke and so again, this is not the reservoir, but you can see it here. But let's assume this was. We had two pairs. We had two here, two here, two here, two here. So we had a total of 16 viscous dampers around the outside connected to the wall. So again, in the left-right direction, we'd have 4 plus 4. We have 8 viscous dampers resisting the load. And when it was in this opposite direction, we had the 4 on this side and the 4 on this side. So we had 8 viscous dampers in each direction resisting the load.
Okay, thanks.
Yeah,
thanks.
Yeah, the stroke I remember was about plus or minus 75, because I was trying to find the curve that I showed you there. I couldn't find it in the specs yesterday, but if I find it, I'll send it through to you.
Okay, because I'm also working a little bit in dampers, and I was interested in this. If you find it, just share it. If not, yes.
Yeah, I will do.
Thank you for a really good and interesting presentation. So that's all from my side.
Okay, Svetlana, you had a question?
Yeah, I have a question, actually, more a comment. First of all, thank you, John, for excellent presentation as always. Regarding this, regarding the viscous dampers, I believe we published the information that about the dampers as a part of the description of the project is available, including this. And we had also 2 more papers published at the World Conferences, both in 2000 and 2004. I believe that we have also some information there. But what I found interesting, and you didn't mention, in fact, by the way, I participated in all these retrofit projects. That was exactly the time I was in Sandville at that time. So I felt that it was very interesting for Kirtland Reservoir, which you just showed now, that there was the feasibility study, if you recall. There was, I would say, a possibility that reservoir could have been, or retrofit would have been avoided. So we did a pushover analysis. That was one of the first, if you recall that, I believe it was for Kirtland, because Kirtland had a moment system. And so we did analysis at the feasibility stage to see what is the performance, expected performance, given the detailing of the structure, which was, I think, back from 1970. And that was also one of the first analysis of that type done for the reservoirs. And at the end, I believe the conclusion was that in spite of being a frame, of course, it was non-ductile. And so this solution with the double frame, so let's say, was done. But it was interesting that the owner, Greater Vancouver, GVRD at that time, was interested to see. Of course, they wanted to avoid, if it is possible. I believe this was for Kirtland, because Kirtland was the only reservoir which had that, even though non-ductile frame system, obviously, but the others were flat slab structures. And according to Canadian codes, flat slab is showstopper. When it comes to seismic, you have to do something. So the others that we showed are that, isn't it? So it's just maybe a little bit of comments. Did you have that situation otherwise? And what do you think about this, kind of trying to save the...
Yeah, no, I think, I think, as we do that more for buildings, for the two-way flat slab. You can try doing pushover analysis, but it's just not going to work. We just don't. They just don't work, Svetlana. And all the reservoirs that we've done, this one with Kirtland, as you say, that's on the screen with columns and beams. It really was a moment frame in one direction. It really was a nice structure, and a pushover analysis there in one direction, as you say, has some value. And again, it didn't work. On On the on these other ones, we've looked at it, and typically there's these old reservoirs just don't have the capacity around the drop panel. They just don't have the capacity to do it. You can put in a topping over the entire roof slab to strengthen that. So there's ways to do it, but then the columns typically don't work, and we've wrapped those with FRP, on some projects. So yeah, it's having a pushover analysis nowadays. We have the tools to do that on seismic upgrade projects, and yeah, you do, as you say, you do a sort of a response spectrum analysis to get a first cut if you're close. Doing a pushover analysis when we do BRBs for seismic upgrades, we always do a pushover analysis to try and get a feel for how they're yielding and where the energy starts to dissipate, and is it distributed the way we like. So yeah, as we start to put in, especially if we're putting in BRBs or friction dampers and those in a retrofit, we do like to do pushover analysis before we jump into the full 3D nonlinear analysis. So yeah, so no, good comment.
Thank you. So I think that we can chat
Yeah.
about all this. And but there are two more papers. Maybe in the I can send you a link. So they are available online free of charge, because all World Conference papers are online. So you just need to find them. I will find them. There were one in 2000 and one in 2004. Still, we had some remaining papers on this topic. So
So let me add those to the references before I send the PDF.
That would be nice, yeah. If they can, they're interested.
And there's a bunch of papers on Little Mountain and all the high volume fly ash and that stuff. I can add that reference as well.
If you can,
because it's all interesting stuff, and there may be a gem of information in those papers for the audience.
Great.
All right.
So any other, Vlado?
Any other questions from the audience? Now's the time. If not, then John, thank you for accepting the invitation, and thanks Svetlana for contacting you. It was an outstanding presentation, and I surely hope that we will have you again in the future with some other types of structures, because from your portfolio, I saw that you're quite widespread on all kinds of challenges in structural engineering. So as a personal note, I really enjoyed today's lecture. Thank you very much.
My pleasure. Yeah, be happy, and I've got to find an excuse to come and visit you in person now.
You should visit us, and we will welcome you in a good style. Serbians are well known for hospitality, so that's I'm sure there will be we hope there will be opportunity for that as well.
All right.
Thank you so much.
Thank you
very much
for
Thank
making
you.
effort.
Have a nice day.
Bye bye. Have a nice day.
And bye bye to everyone. Hvala.